Okay, think about this for a second. You plug in your phone charger,
Uh,
right? Or maybe you just flick a light switch and bam, the room's lit up.
yeah, it happens all day, every day.
Exactly. It's so normal, so mundane. We almost never think about the incredible stuff happening behind the scenes.
Mm.
It's not just generic electricity, is it? It's actually one of two specific types: direct current, DC, or alternating current, AC.
It really is pretty amazing when you stop and think about it, how much we rely on it, how it's just woven into everything we do. And yeah, most people are using both AC and DC constantly without even realizing they're different.
Which brings us straight to the big puzzle we're tackling in this deep dive.
Yeah.
If, so many of our gadgets now, phones, computers, all the stuff we use constantly actually run on DC,
Yeah, that's true.
then why?
Yeah.
Why is the whole massive system, the power plants, the big transmission lines, the outlet right there in your wall, why is that all based on AC? It feels, I don't know, kind of backward, doesn't it? Like a real historical mystery.
It does seem counterintuitive at first glance, but the answer, well, it's not just about which one's technically better in a vacuum. It's all tangled up with history, big inventions, fierce business rivalries, and really what was possible, technologically speaking, way back when this all started.
Right. So that's our mission today. We're going to sort of pull back the curtain on this whole AC-DC story. We'll look at that famous or infamous current war
Oh yeah, that was quite something.
and figure out the real reasons AC became the standard. But then we'll also look at how DC is, surprisingly, making a big comeback now. So if you've ever wondered, why the wall socket is AC or why your phone charger has that chunky brick,
Yeah, converter, yeah.
we're going to get to the bottom of it for you today. Okay, so before we really dive into that historical battle and why things shook out the way they did, we probably need to make sure we're all crystal clear on the basics. What is the actual difference between AC and DC?
Yeah, that's essential. Because understanding the core difference really highlights why that question you raised, why AC for the grid when our devices use DC, is so interesting.
It feels like there's a big why just hanging there.
Absolutely. And like I said, grasping why AC dominates means looking beyond just the pure tech specs. You have to think about the moment in history, the economics, the limitations people were working under back then. But yeah, let's start simple.
Perfect. Let's kick off with direct current, DC. What's the simple explanation?
Direct current is, well, it's pretty much what it sounds like. The electricity flows in just one direction, constantly, steadily.
Called a one-way street.
Exactly like a one-way street for the electrons. They just keep moving forward from a higher potential to a lower one, never turning back. It's just a continuous, steady push like water flowing down a river, always in the same direction.
Okay, I can picture that. A constant, unwavering flow. That's DC.
Yep. And you find DC everywhere, even if you don't label it that way. Your standard AA battery, that's DC. Your car battery, DC.
Ah, right. Batteries. Makes sense.
And the power coming through a USB cable to charge your phone or run your laptop, that's DC too. Even a lot of modern LED lights actually use DC internally after converting the power from the wall.
Got it. So very stable, predictable power.
Yeah.
Now, flip the coin. What about alternating current? AC. How's that different from the steady DC flow?
Alternating current is where things get a bit more dynamic. Instead of that constant one-way flow, AC periodically reverses its direction. The electrons don't just march forward.
So they go back and forth.
Exactly. Think of it like the tides in the ocean flowing in, then flowing out. Or maybe like a seesaw, constantly going up and down. The electrons move one way for a bit, then they reverse and move the other way, back and forth, back and forth.
Okay, so not a one-way street, but more like
Yeah.
traffic that completely switches direction every fraction of a second.
That's a good way to put it. It's a rhythmic cycle. In most places, that reversal happens 50 or 60 times every single second, so it's a very rapid oscillation.
That sounds, well, inherently more complicated, maybe less stable.
In terms of the electron movement, yes, it's more dynamic, but AC is just as common in our lives, just in different places. The power outlets in your house, they deliver AC.
Right, wall sockets.
Those huge power lines you see strung up on giant towers across the countryside, carrying AC. And, this is key, the electricity generated at almost all power plants, whether it's hydro, wind, coal, nuclear, it's almost always generated initially as AC.
Okay, so laying it out like that really drives home the question, doesn't it? We've got all our modern electronics, phones, laptops running on DC.
Internally, yes.
But the entire grid, from the power station miles away right down to the socket in the wall, is AC. Why did we end up with that setup? It seems like we chose the wrong one for the modern world almost.
It really does feel like a historical accident sometimes. But the reason, the deep reason, isn't just about technical preference today. It's rooted in the history, in the specific tech available, and maybe more importantly, the tech that wasn't available back in the late 1800s. The world of electrical engineering then was, well, a completely different ballgame.
And those differences, those early challenges, threw us right into one of the biggest tech showdowns ever, the Battle of the Currents. All right, we're back. We've got the basics of AC and DC down, which perfectly sets the scene for this epic clash of technologies and personalities. Let's really step back in time now. Can you paint a picture for us? What was it like in the late 1880s when electricity was just starting?
Oh, absolutely. Imagine a world just buzzing, literally and figuratively, with excitement. Electric light wasn't a given. It was this new, almost magical invention capturing everyone's imagination. Cities were booming, factories needed more power.
A time of huge change.
Massive change. And the big question wasn't just if we could make electricity, but how could we get it to people? How could we distribute it reliably, affordably, everywhere? People were basically deciding right then how the future would be lit and powered. And two very, very different ideas about how to do that were about to collide head on.
And championing these two clashing visions were some real titans of invention and industry. On one side, probably the most famous inventor ever, Thomas Edison.
Yes, Edison, the Wizard of Menlo Park. A brilliant inventor, no doubt, especially known for perfecting the practical incandescent light bulb. That really lit the fire, so to speak.
Right, yeah.
And his vision was all about direct current. He'd already built DC power stations, small ones, designed to power a neighborhood, basically. He genuinely believed DC was safer, more stable, just better. He had a lot invested in it already, too, financially and reputationally.
Okay, so Edison's camp is firmly DC. Who was on the other side, pushing for AC?
That's where Nikola Tesla comes in, often called the father of AC. An incredible mind, maybe a bit more eccentric than Edison. He developed a much more advanced AC system. But Tesla wasn't really the businessman Edison was.
So he needed a partner.
Exactly. And he found one in George Westinghouse. Westinghouse was already a big name, a successful industrialist. He'd made his fortune with railway air brakes. He saw the massive potential in Tesla's AC patents, bought them, and really threw his company's weight behind commercializing AC. So you had Tesla's genius paired with Westinghouse's business power. That combination was formidable.
So this wasn't just inventors tinkering in labs. It became a full-blown war.
Oh, absolutely. The current war. It was brutal. It wasn't just technical arguments. It was fierce economic competition, political maneuvering, lobbying, even some pretty nasty PR campaigns. They were fighting for total dominance to decide which system would power America and ultimately the world.
Nasty PR. What kind of things happened?
Well, Edison, feeling threatened by AC's potential, went on the offensive. He tried to paint AC as inherently dangerous, deadly even. His team staged these quite gruesome public demonstrations, electrocuting stray animals, dogs, cats, even horses, using AC power.
Seriously? That's horrifying.
It was. They even got involved in the development of the electric chair, using AC specifically to associate AC with death in the public mind. It was a deliberate, calculated fear campaign. Edison stood to lose everything if DC was replaced.
Wow, that really shows how high the stakes were. But despite Edison's efforts and his head start, his DC system had a fundamental problem, didn't it?
Yeah.
What was its big weakness back then?
The critical flaw, the real Achilles heel for Edison's DC, especially for powering large areas, was that you couldn't easily change its voltage. You couldn't efficiently step it up to high voltage for transmission or step it down for use.
Okay, you couldn't change the electrical pressure, so to speak. What did that mean in practice for getting power to people?
It meant DC power plants had to be really, really close to the customers. We're talking maybe a mile radius maximum.
Well, that's tiny.
It is. So if you wanted to power a whole city with DC, you'd need a power plant practically on every other block. Imagine the cost, the real estate, the inefficiency. And trying to send that low voltage DC even a few miles down a wire resulted in huge power losses. The energy just turned into heat in the copper wires and disappeared.
So it's just completely impractical for anything beyond a very small, dense area. You couldn't build a regional or national grid with that kind of limitation.
Exactly. It severely limited how far DC could reach and how big the system could scale. It just wasn't economical or feasible for widespread electrification.
Okay, so here's the turning point. This is where Tesla and Westinghouse's AC system came in with a solution to that exact problem. What was their breakthrough?
The absolute game changer for AC was its perfect marriage with a device called the transformer. A relatively simple device, really, just coils of wire around an iron core, but it could do something DC couldn't. easily and very efficiently change the voltage of AC power.
Right, the transformer. How did that simple device solve the distance problem that plagued DC?
Because you could use transformers, you could build big, efficient AC power plants far away from cities, maybe at a waterfall like Niagara Falls, which was a famous early example. You generate the AC power, then use a transformer to step up the voltage incredibly high, hundreds of thousands of volts.
Why so high?
Because sending power at super high voltage dramatically reduces the amount of energy lost in the transmission wires over long distances. Less current is needed for the same amount of power. Then, when the power got close to the towns and homes where it was needed, you'd use other transformers to step down the voltage to safe, usable levels like the 120 or 220 volts we use today.
Ah, I see. So you could generate power efficiently far away, send it long distances without much loss, and then safely bring it down for people to use. That completely changes the economics, doesn't it?
Completely. Suddenly, one large power plant could serve a huge area hundreds of miles away. It made building a widespread, interconnected power grid economically viable. That ability to efficiently transmit power over long distances using transformers was the killer advantage.
So despite Edison's fame and his fierce fight, the sheer practicality and cost-effectiveness of AC transmission just won out.
Ultimately, yes. AC's ability to be transformed and sent efficiently over long distances, combined with the robustness of AC equipment, which we'll get into, meant it was the superior choice for building the large-scale electrical infrastructure the world needed. The current war had a clear winner, and AC became the standard.
Okay, so the history is fascinating. The current war really set the stage. But AC didn't just win back then. It stayed the dominant standard for over a century. There must be more to it than just winning that initial battle. What are the enduring technical reasons why AC works so well for our grid?
That's a really important point. History decided the winner initially, but AC's fundamental properties and the technologies built around it are why it's remained the backbone for so long. It wasn't just a historical fluke.
Right. So let's dig into those reasons. What's advantage number one? You mentioned it already, but let's explore it more.
It really does come back to that core strength. Easy voltage transformation. The transformer is the heart of the AC grid's flexibility. It's what makes the whole system practical on a large scale.
How does AC actually allow that? Can we understand the why a bit more without getting too technical?
Sure. Remember how AC constantly reverses direction. That means its voltage is always changing, rising, falling, reversing. This constant change is key. It creates a changing magnetic field around the wire.
Okay.
Now, a transformer basically has two coils of wire wrapped around an iron core, but they aren't electrically connected. The changing magnetic field from the AC in the first coil induces a current in the second coil. That's electromagnetic induction.
Ah, like physics class.
Exactly, Faraday's law, basically.
Mm.
And here's the clever part. If you change the number of wire turns in the second coil compared to the first, you change the voltage. More turns steps the voltage up, fewer turns steps it down, and it does this incredibly efficiently with very little energy loss. DC, being constant, doesn't create that changing magnetic field, so simple transformers just don't work with it.
Got it. So that constant change in AC is what makes the magic happen in the transformer. Walk us through that journey again, power plant to my house. How do transformers make that work?
Okay, so power is generated at the plant, maybe at, say, 25,000 volts. Right away, big transformers step it way up, maybe to 400,000 volts, or even higher for long-distance transmission lines.
Those huge towers we see everywhere.
Yep. Sending it at that super high voltage means less current is needed for the same power, which drastically cuts down energy lost as heat in the wires over hundreds of miles. It's all about efficiency.
Makes sense. Then what?
As it gets closer to towns and cities, it hits a substation. More transformers there step the voltage down, maybe to around 10,000, 50,000 volts for distribution around the region.
Still pretty high.
Still high, yeah. Then it travels along smaller lines until it gets near your neighborhood. There, you'll see smaller transformers maybe on a pole or in one of those green metal boxes on the ground. Those step it down one last time to the final voltage that comes into your house, like 120 volts or 220 volts, depending on where you live.
And this whole up and down voltage journey relies on these transformers, which are efficient and reliable for AC.
Exactly. Transformers are amazing pieces of engineering, incredibly efficient, often over 99%, very robust. They last for decades with minimal maintenance. Trying to do that kind of large-scale voltage conversion with DC back in the day was practically impossible. You needed complex, bulky, inefficient rotating machinery, or later semiconductor devices that just didn't exist yet. So that ease of voltage change is absolutely fundamental to why our grid is AC. We wouldn't have widespread power without it.
Okay, that's a huge advantage.
Yeah.
But you mentioned earlier that the machines themselves were also better suited for AC, both making it and using it.
Yes, that's the second major piece of the puzzle. AC generators and motors were, and largely still are, simpler and more robust than their DC counterparts, especially in the early days.
How so? Let's start with generators making the electricity.
AC generators, or alternators, typically use a rotating magnet inside stationary coils of wire. It's a relatively simple, elegant design. Because the main power-generating coils don't move, you don't need complicated connections to get the high current out. This makes them very durable, easy to maintain, and great for generating huge amounts of power from spinning turbines, whether driven by water, wind, or steam.
And DC generators were more complicated.
Much more complicated back then. To get that steady, one-direction current, DC generators needed something called a commutator and brushes. These were physical contacts, carbon blocks, rubbing against rotating copper segments that mechanically switched the connections as the generator spun.
That sounds like a recipe for problems.
It was. You had constant friction, sparks flying, the brushes and commutator wearing down quickly, creating conductive dust. It meant frequent, messy maintenance. Imagine trying to keep hundreds of those running reliably, 247 in a city power station. It was a maintenance nightmare compared to the simpler AC generators.
Okay, that makes sense for generating power. What about using it? Motors. You said most electricity powers motors.
Right. Think about it. Fans, pumps, washing machines, refrigerators, factory machines, elevators. Motors are everywhere. And the most common type of AC motor, the induction motor, which Tesla also played a huge role in developing, is a marvel of simplicity and ruggedness.
How did it work?
Basically, the AC power fed into stationary coils in the motor creates a rotating magnetic field. This field induces currents in the rotor, the spinning part, creating another magnetic field, and the interaction between these fields makes the rotor spin. The beauty is there are no direct electrical connections needed to the spinning part for the main power.
No brushes again?
Exactly. No brushes, no commutator. That means no sparks, much less wear and tear, longer life, less maintenance. Early DC motors needed those same problematic brushes and commutators as the generators. So for industry and eventually homes, AC motors were just more practical, reliable, and cheaper to run long-term.
So easier to make the power, easier and more reliable to use the power for work. That's a pretty compelling case for AC.
It's a very powerful combination. And it leads into the third advantage, which is maybe a bit more subtle, but still really important for the whole system.
Okay, what's the third one?
It's about how easily AC systems connect together and work with all those motors. Since most of the motors out there, especially the big industrial ones, run on AC.
Right, because they're simpler and more reliable.
The AC electricity from the power plant can be used directly by them. There's no need for conversion at the point of use. It simplifies the whole chain enormously. Also, connecting multiple AC power plants together to form a large, stable grid is relatively straightforward. They naturally synchronize their frequency, that 50 or 60 cycles per second rhythm we talked about. This makes the grid stable and allows power sharing across vast regions.
And if the grid was DC, what would happen with all those AC motors?
Well, think about it. Every single factory motor, every air conditioner, every washing machine would need its own built-in converter and inverter to change the grid's DC back into AC for the motor to use.
Wow, that sounds incredibly inefficient and expensive. Billions of extra converters everywhere.
Exactly. It would add enormous cost, complexity, points of potential failure, and energy losses from all those conversions. The fact that AC generation matched perfectly with the preferred type of motor for most applications was a massive practical advantage that streamlined the entire electrical ecosystem. It just made everything work together more seamlessly.
Okay, so AC clearly won the war, and for really solid technical reasons, easy voltage change, simpler generators and motors, seamless integration, it seems like a closed case. But the story isn't quite over, is it? You mentioned DC is making a comeback. How is that happening?
You're right, it's definitely not a closed case. While AC is still the king of the grid for general distribution, technology hasn't stood still. There have been huge advances, especially in electronics, that are making DC look very attractive again for certain very important applications. It's having a real renaissance.
A DC renaissance.
Yeah.
So what are the advantages DC offers now that maybe weren't relevant or achievable before?
Well, one really big one, somewhat ironically, is in very long-distance transmission. For extremely long power lines, say over 500 miles, or especially for underwater cables connecting countries, or offshore wind farm.
Right, those are becoming more common.
High voltage direct current, or HVDC, can actually be more efficient than AC. It loses less power over those extreme distances.
Wait, how? I thought AC won because it was better for long distances.
It was because of transformers allowing high voltage. But AC has some inherent losses related to its alternating nature that DC doesn't. Things like skin effect, where the AC current crowds near the surface of the wire, increasing resistance, and reactive power losses related to the capacitance and inductance of long lines. DC doesn't have frequency, so it avoids those specific AC loss mechanisms. For really long hauls, HVDC's lower line losses can outweigh the conversion losses at each end.
Okay, so for super long distances, DC can actually win on efficiency now.
Yeah.
Are there other modern DC advantages?
Another is potentially lower insulation requirements in some cases. Since DC voltage is constant, not peaking like AC, the insulation might not need to withstand quite as high a peak voltage for the same average power delivery. Also, linking two separate AC grids that aren't synchronized, maybe running at slightly different frequencies or phases, is very difficult with AC, but relatively easy with an HVDC link acting as a buffer between them.
Interesting. But if these advantages existed, why didn't HVDC take off earlier? What was the missing piece?
The missing piece was the technology to handle the DC at high power levels efficiently. Remember, the big historical problem for DC was changing voltage and switching high power. Simple transformers don't work.
Right.
But this is where modern electronics have completely changed the game. The invention and continuous improvement of high-power semiconductor devices, things like thyristors, and especially newer devices like IGBTs, insulated gate bipolar transistors, these are essentially very fast, very powerful electronic switches.
Okay, semiconductors, like in computers, but much bigger.
Exactly. Think of them as the muscle behind modern power electronics. They allow us to convert AC to DC, that's rectification, and crucially convert DC back to AC inversion very efficiently, even at hundreds of thousands of volts and handling millions of watts. We can now chop up, control, and reshape DC power in ways that were simply unimaginable during the current war. These solid-state devices replace the need for bulky, inefficient mechanical converters.
So the tech finally caught up and solved DC's biggest historical weakness.
Precisely. What was once a fundamental roadblock is now manageable, thanks to decades of semiconductor research and development. This technological leap is what enables things like efficient HVDC transmission and opens the door for other DC applications.
And we see DC everywhere in our daily lives now, too, right? It's not just these huge transmission lines.
Oh, absolutely. Look at almost any piece of consumer electronics. Your laptop, your phone, your tablet, your flat-screen TV, LED lighting, they all internally run on low-voltage DC.
So that power adapter, the brick.
That brick is basically a mini power plant in reverse. It takes the 120 or 220 volts AC from your wall, uses semiconductors to rectify it down to DC, and then regulates it to the specific low voltage, maybe 5 volts, 12 volts, 19 volts, that the device's sensitive circuits actually need.
And USB is a perfect example of standardized DC, isn't it?
USB is a fantastic example. Universal Serial Bus. It started for data, but it quickly became a nearly universal standard for delivering low-voltage DC power to charge and run countless gadgets. Billions of devices use USB power. It really shows how convenient and pervasive low-voltage DC has become in our personal tech world.
So putting it all together, what's the future look like? AC is still the grid backbone, but DC is clearly making serious inroads.
It's a fascinating convergence. We're definitely seeing more HVDC projects for long-distance bulk power transfer and grid interconnection. That's a growing field. And think about renewable energy.
Like solar panels.
Exactly. Solar panels naturally produce DC power. Batteries, which are becoming critical for storing energy from intermittent sources like solar and wind, store energy as DC. Right now, we often convert that DC to AC to feed it into the grid, then maybe convert it back to DC inside our homes for our devices. That's multiple conversion steps, each with some energy loss.
Seems inefficient.
It is. So there's a lot of interest in developing more direct DC pathways, maybe DC microgrids within buildings or campuses, integrating solar, batteries, and DC loads like LED lighting and electronics more efficiently. Maybe even DC circuits directly in our homes alongside AC ones someday.
So DC isn't replacing AC wholesale, but it's finding powerful new roles alongside it, filling niches where it offers real advantages thanks to modern tech.
That's exactly right. It's becoming a vital complement to the AC grid, enabling greater efficiency in specific areas like long-distance transmission, renewable integration, and powering our digital lives. The comeback is real, driven entirely by technological innovation overcoming historical limitations.
Wow, what a journey we've been on today. We started with something as simple as plugging in a phone, and we ended up deep in this epic current war between Edison and Tesla Westinghouse.
Yeah, it's a story with huge personalities and massive stakes.
And we saw clearly why AC won that initial battle, mainly because transformers made it easy and efficient to change voltage, which was crucial for sending power over long distances. Plus, AC generators and motors were just simpler and tougher back then.
Those were the decisive factors, absolutely. They allowed for the creation of the large, interconnected grids we rely on.
But then the story took a twist. We learned that DC, the original runner-up, is making this incredible comeback in the 21st century.
Thanks entirely to those amazing advances in semiconductor power electronics, they finally gave DC the tools it needed to handle high power efficiently.
Right, making it super efficient for things like very long-distance HVDC lines and perfect for integrating solar power and batteries. And, of course, it's the native language of all our gadgets.
Our phones, laptops, data centers, they all think in DC.
So the next time you flip that switch, or plug in that charger, or even just see those giant transmission towers marching across the hills, you'll know there's a massive story behind it. It's not just power. It's a whole system shaped by historical battles, brilliant inventions, and technology that's still evolving right now.
It really puts it in perspective, doesn't it? How decisions made over 100 years ago, based on the tech they had then, still shape our world, but also how new inventions are constantly forcing us to rethink those old assumptions.
Which brings us to our final thought, something for you to chew on. As our lives get filled with more and more things that run on DC, our computers, phones, TVs, LED lights, maybe soon our electric car is charging at home.
And as we get more power from DC sources like solar panels on our roofs,
What does the future hold? Could we see homes eventually wired with both AC and DC outlets side by side, maybe dedicated USB-C power outlets everywhere? Or could we see a bigger shift, maybe localized DC microgrids powering our neighborhoods more efficiently from local solar and batteries? What would that future actually look like, and how would it change how we interact with the energy that powers everything we do?